Introduction to Analytical Chemistry. Analytical chemistry facilitates investigations of chemical composition of substance. It uses the instruments and method to separate, identify, and quantify the matter under study. The analysis thus provide chemical or physical information about sample. Analysis may be Analysis may be qualitative or quantitative. Qualitative analysis is concerned with the detection of the presence or absence of element in compounds and mixture of compounds. Quantitative analysis deal with the determinations of the relative proportions of element in compound and mixture compounds. Remember, the branch of chemistry which deals with study of separations, identifications, qualitative and quantitative determinations of the compositions of different substances is called analytical chemistry. Importance of analytical chemistry. The course of analytical chemistry extend the knowledge acquired by the students in studying general, inorganic and organic chemistry. Chemical analysis is one of the most important methods of monitoring the composition of raw materials, intermediate and finished products, and also the composition of air in streets and premises of industrial plants. In agriculture, chemical analysis is used to determine the composition of soils and fertilizers. In medicine, to determine the composition of medicinal preparations. Analytical chemistry has application in forensic science, engineering, and industry. Industrial process as a whole and the productions of new kind of materials are closely associated with analytical chemistry. Analytical chemistry consists of classicals, wet chemical methods, and modern instrumental methods. Analysis. Analysis is carried out on a small sample of the material to be tested and not on the entire bulk. When the amount of a solid or liquid sample is a few grams, the analysis is called semi-microanalysis. It is of two types, qualitative and quantitative. Classical qualitative analysis methods include separations such as precipitation, extraction, and distillation. Identification may be based on difference in color, odor, melting point, boiling point, and reactivity. Classical quantitative methods contain of volumetric analysis, gravimetric analysis, etc. Chemical method of qualitative analysis. Chemical analysis of a sample is carried out mainly in two stages. By the dry method, in which the sample under test is not dissolved, and by the wet method, in which the sample under test is first dissolved and then analyzed to determine its composition. The dry method is usually used as preliminary test in the qualitative analysis. The semi-micro qualitative analysis is carried out using apparatus such as test tubes, beakers, evaporating dish, crucible, spot plates, water glass, wire gauze, wire bath, burner, blowpipe, pair of tongs, centrifuge, etc. The qualitative analysis of organic and inorganic compound involve different types of tests. The majority of organic compounds are composed of a relatively small numbers of elements. The most important ones are carbon, hydrogen, oxygen, nitrogen, sulfur, halogen, phosphorus. Elementary quantitative analysis is concerned with the detection of the presence of these elements. The identifications of an organic compound involve tests such as detection of functional group, determinations of melting or boiling point, etc. The qualitative analysis of simple inorganic compound involved detection and confirmation of cationic and anionic species, basic and acid radicals in them. Chemical method of quantitative analysis. Call it quantitative analysis of organic compound involve methods such as determination of percentage constituents elements, concentration of a known compound in the given sample, etc. Quantitative analysis of simple inorganic compound involve methods based on decomposition reaction, gravimetric analysis, and the progress of reaction between two solutions till its completion, titrimetric or volumetric analysis, etc. The quantitative analytical methods involve measurement of quantities such as mass and volume by means of some equipments or apparatus such as weighing machine, burette. 2.3 Mathematical operations and error analysis. The accuracy of measurement is of a great concern in analytical chemistry. Also, there can be intrinsic error in the analytical measurement. The numerical data obtained experimentally are treated mathematically to reach some quantitative conclusions. Therefore, an analytical chemist has to know how to report the quantitative analytical data, indicating the extent of the accuracy of measurements, perform the mathematical operations, and properly express the quantitative error in the results. In the following subsections, we will consider these aspects related to measurements and calculations. Scientific notation, exponential notation. A chemist has to deal with numbers as large as 602, 200, 000, 000, 000, 000, 000, 000, or the molecule of 2 gram of hydrogen gas, or as small as 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 in mathematical operations, scientific notations, that is, exponential notations, are used. Here, any number can be represented into a form of n multiplied by 10 raised to n, where n is an exponent having positive or negative values. Capital N can vary 1 smaller or equal to capital N, which is smaller than 10. Thus, we can write the above values as 6.022 10 raised to 23 and 1.66 10 raised to minus 24 gram. The number 123.546 become 1.23546 multiplied by 10 raised to 2 in scientific notation. Note that while writing it, we have moved the decimal to the left by 2 places, and same is the exponent 2 of 10 in the scientific notation. Similarly, 0.00015 can be written as 1.5 10 raised to minus 4. Problem 2.1. By adding 5.555 10 raised to 4 and 6.95 10 raised to 3, first the exponent is made equal. Thus, 5.55 10 raised to 4 plus 0.695 10 raised to 4. Then these numbers can be added as follows. 5.55 plus 0.695 multiplied by 10 raised to 4 is equal to 6.245 multiplied by 10 raised to 4. Problem 2.2. The subtractions of two numbers can be done as shown below. 3.5 10 raised to minus 2 minus 5.5 10 raised to minus 3. 3.5 10 raised to minus 2 minus 0.58 10 raised to minus 2. 3.5 minus 0.58 is multiplied by 10 raised to minus 2 is 2.92 10 raised to minus 2. Here the decimal has to move 4 places to right, and minus 4 is the exponent in the scientific notation. Now let us perform mathematical operation on a number expressed in scientific notations. 2.3 5.6 10 raised to 5 multiplied by 6.9 10 raised to 8. 5.6 multiplied by 6.9 10 raised to 5 plus 8 is give 10 raised to 13th. 5.6 multiplied by 6.9 is 38.64 10 raised to 13. So equal to 3.86 for 10 raised to 14. Problem 2.4. 9.8 10 raised to minus 2 multiplied by 2.5 10 raised to minus 6. So it will give 9.8 multiplied by 2.5 10 raised to minus 2 plus minus 6 will be 9.8 multiplied by 2.5 multiplied by 10 raised to minus 2 minus 6. It will give 24.50 multiplied by 10 raised to minus 8 equal to 2.45 10 raised to minus 7. Addition and subtractions. To perform additions operation, first the numbers are written in such a way that they have the same exponent. The coefficients are then added. Problem 2.1 and 2.2. Multiplication. The rules for the multiplication of exponential number can be well explained from the solved problem 2.3 and 2.4. Precision and accuracy of measurement. Aim of any measurement is to get the actual value called true value except the value of quantity. Nearness of the measured value to the true value is called the accuracy of measurement. Large the accuracy, smaller the error. Accuracy depends upon the sensitivity or least count. The smallest quantity that can be measured of the measuring equipments. Consider for example a burette reading of 10.2 ml for all the three situations in the figure 2.1. The reading would be noted as 10.2 ml. It means that there is an uncertainty about the digit appearing after the decimal point in the reading 10.2 ml. This is because the least count of the burette is 0.1 ml. The meaning of the reading 10.2 ml is that the true value of the reading lies between 10.1 ml and 10.3 ml. This is indicated by writing 10.2 plus minus 0.1 ml. Here the burette readings has an error of plus minus 0.1 ml. Figure 2.1. Error may be expressed as absolute or relative error. Absolute error is equal to observed value minus true value. Relative error is generally a more useful quantity than absolute error. Relative error is a ratio of an absolute error to the true value. It is expressed as a percentage. Relative error is equal to absolute error upon true value multiplied by 100%. There can be error in a measurement due to a number of reasons, including inefficiency of person doing measurements. Three possibility of a burette reading is 10.2 ml. Multiple reading of the same quantity are noted to minimize the error. If the reading match closely, they are said to have high precisions. High precision implies reproducibility of the reading. High precision is a prerequisite for high accuracy. Precision is expressed in terms of deviations. An absolute deviation is a modulus of the difference between an observed value and arithmetic mean for the set of several measurements made in the same way. It is a measure of absolute error in the repeated observations. The absolute deviations is equal to observed value minus mean. Arithmetic mean of all the absolute deviation is called the mean absolute deviation in the measurements. The ratio of mean absolute deviation to its arithmetic mean is called relative deviations. Relative deviations is equal to mean absolute deviations upon mean multiplied by 100%. In laboratory experiment, 10 gram potassium chlorate sample on decomposition gives following data. The sample contained 3.8 gram of oxygen and actual mass of oxygen in the quantity of potassium chlorate is 3.92 gram. Calculate absolute error and relative error. Solution. Observed is 3.8 gram and accepted value is 3.92 gram. Is absolute error equal to observed value minus true value? It is equal to 3.8 minus 3.92 gives minus 0.12 gram. The negative sign indicates that your experimental result is lower than the true value. The relative error is equal to absolute error upon true value multiplied by 100% is equal to minus 0.12 upon 3.92 multiplied by 100% is equal to minus 3.06%. The three identical samples of potassium chloride are decomposed. The mass of oxygen is determined to be 3.87 gram, 3.95 gram and 3.89 gram for the set. Calculate absolute deviation and relative deviation. Solution. Mean equal to 3.87 plus 3.95 plus 3.89 upon 3 is equal to 3.90. Average deviation of a set of measurement. Sample 1. Mass of oxygen is 3.87 gram. Deviation is 0.03 gram. Sample 2 is mass of oxygen 3.95 gram. Deviation is 0.05 gram. Sample is 3.89 gram. Deviation is 0.01 gram. Mean absolute deviation value is 0.03. Absolute deviation's formula is observed value minus mean. Mean absolute deviation is equal to plus minus 0.03 gram. The relative deviation is equal to mean absolute deviation upon mean multiplied by 100% is equal to 0.03 upon 3.9 multiplied by 100% is equal to 0.8%. Significant figure. Uncertainty is measured value lead to uncertainty in calculated results. Uncertainty in a value is indicated by mentioning the number of significant figure in their value. Consider the column reading 10.2 plus minus 0.1 ml recorded on a burette having the least count of 0.1 ml. Here it is said that last digit 2 in the reading is uncertain. Its uncertainty is plus minus 0.1 ml. On the other hand, the figure 10 is certain. The significant figure in measurements or results are the number of digits known. This certainty plus one uncertain digit. In a scientific experiment, a result is obtained by doing calculations in which value of a number of quantitatives measured with equipment of different least count are used. Following the rules are to be followed during such calculations. Rules for deciding significant figure. All non-zero zero digits are significant. Example 127.34 gram contain 5 significant figures which are 1, 2, 7, 3 and 4. All zero between two non-zero digits are significant. Example 120.007 m contains 6 significant figures. Third, zeros on the left of the first non-zero digits are not significant. Such a zero indicates the position of the decimal point. For example, 0.025 has two significant figures. 0.005 has one significant figure. Fourth, zero at the end of a number are significant if they are on the right side of the decimal point. Terminal zero are not significant if there is no decimal point. This is because the least count of an instrument contains decimal point. For example, 0.400 gram has three significant figures. The measurement here indicates that it is made on a weighing machine having least count of 0.001 gram. Significant figure also indicated in scientific notation by mean of decimal point. For example, the measurement 400 gram has one significant figure. The measurement 4 multiplied 10 raised to 2 gram has two significant figures, whereas the measurement 4 10 raised to 2 gram has three significant figures. The zero after decimal point in these cases indicate the release count of the weighing machine are 1 gram, zero point 0.1 gram and 0.01 gram respectively. In number written in scientific notation, all digits are significant. For example, 2.035 10 raised to 2 has four significant figures and 3.25 multiplied by 10 raised to minus 5 has three significant figures. Problem 2.7. How many significant figures are present in the following measurements? 4.065 m, b 0.32 gram, c 57.98 cm cube, d 0.02 second, e 4.010 raised to minus 4 kilometer, f 604.0820 kg, G 307.100, 10 raised to minus 5 centimeter. So A is 4, B is 2, C is 4, D is 1, E is 2, F is 7, G is 6. In general, a quantity measured with an instrument of smaller least count will have more significant figure and will be more accurate than when measured with an instrument of larger least count. Calculation with significant figure. When performing calculations with measured quantities, the rules is that the accuracy of the final result is limited to the accuracy of the least accurate measurement. In other words, the final result cannot be more accurate than the least accurate number involved in the calculation. Rounding off. The final results of calculations often contain figures that are not significant. When this occurs, the final result is rounded off. The following rules are used to round off a number to the required number of significant figures. If the digits following the last digit to be kept in less than 5, the last digit is left unchanged. Example 46.32 round off to two significant figure is 46. If the digit following the last digit to be kept is 5 or more, the last digit to be kept is increased by 1. Example 52.87 rounded to three significant figure is 52.9. Rounded off each of the following to the number of significant digits indicated: A 1.22322 digit, B 12.5623 digit, C is 122.17 to 4 digit, D is 2315.5 to 3 digit. Answer. First, 1.2, the third digit is less than 5, so we drop it all the other to its right. Second, 12.6, the fourth digit is greater than 5, so we drop it and add 1 to the third digit. Third, 1 to 2.2, the fifth digit is greater than 5, so we do it and add 1 to the fourth digit. Fourth, 232, the fourth digit is 5, so we drop it and add 1 to the third digit. Determination of molecular formula. Molecular formula of a compound is the formula which indicate the actual number of atoms of the constituent element in a molecule. It can be obtained from the experimentally determined value of a percent, elemental compositions and molar mass of that compound, percent composition and empirical formula. Compounds are formed by chemical combination of different elements. Quantitative determination of the constituent element by suitable method provide the percent elemental composition of a compound. If the percent total is not 100, the difference is considered as a percent oxygen. From the percent composition, the ratio of the atom of the constituent element in the molecule is calculated. The simplest ratio of atom of the constituent element in molecule is called the empirical formula of the compound. Molecular formula can be obtained from the empirical formula if the molar mass is known. The molar mass of the substance under the examination is determined by some convenient methods. The following example illustrate this sequence. Problem 2.9. A compound contains 4.07% hydrogen, 24.27% carbon, and 71.65% chlorine by mass. Its molar mass is 98.96. What is its empirical formula? Atomic masses of hydrogens, carbon, and chlorines are 1.008, 12.00, and 35.453 U respectively. Solutions. Step 1. Check whether the sum of all the percentage is 100. 4.07 plus 24.27 plus 71.65 is equal to 99.99 equal to 100. Therefore, no need to consider presence of oxygen atom in the molecule. Step 2. Conversion of mass percent to gram. Since we are having mass percent, it is convenient to use 100 gram of the compound. As the starting material does in the 100 grams sample of the above compound, 4.07 gram hydrogen, 24.27 gram carbon and 71.65 gram fluorine is present. Continue on next page. Step 3. Convert into number of moles of each element. Divide the masses obtained above by respect to atomic masses of various elements. Moles of hydrogen is equal to 4.07 gram upon 1.008 gram is equal to 4.04. Moles of carbon 24.27 gram upon 12.01 gram gives 2.0225. Moles of chlorine is 71.65 gram upon 35.453 gram gives 2.021. Step 4. Divide the mole value obtained above by the smallest value among them. Since 2.021 is smallest values, divisions by it gives a ratio of 2 is to 1 is to 1 for H is to C is to Cl. In case the ratio are not whole number, then they may be converted into whole number by multiplying by the suitable coefficient. Write the empirical formula by mentioning the number after writing the symbol of respect to element. CH2Cl is thus the empirical formula of the above compound. Writing molecular formula. Determine empirical formula mass and the atomic masses of various atoms. Present in the empirical formula for CH2Cl, empirical formula mass is 12.01 plus 2 multiplied 1.008 plus 35.453 is equal to 49.48 gram. Divide molar mass by empirical formula mass. Molar mass upon empirical formula mass is equal to 98.96 gram upon 49.48 gram. R is equal to 2. C. Multiply empirical formula by R obtained above to get the molecular formula. Molecular formula is equal to R multiplied by empirical formula. Molecular formula is 2 multiplied by CH2Cl, that is C2H4Cl2. Problem 2.10. A compound with the molar mass 159 was found to contain 39.62% copper and 20.13% sulfur. Suggest molecular formula for the compound. Atomic masses is copper equal to 63, sulfur is equal to 32 and oxygen is equal to 16. Solution. Percent copper plus percent sulfur is equal to 39.62 plus 20.13 is equal to 59.75. This is less than 100%. Hence, compound contain adequate oxygen, so that total percentage of element is 100%. Hence, percent of oxygen is equal to 100 minus 59.75 is equal to 40.25%. Moles of copper is equal to percent of copper upon atomic mass of copper is equal to 39.62 upon 63 is 0.629. Moles of sulfur is equal to percent of sulfur upon atomic mass of sulfur is equal to 20.13 upon 32 is equal to 0.629. Moles of oxygen is 2.516% of oxygen upon atomic mass of oxygen is equal to 40.25/16. Hence, the ratio of number of moles of copper is to sulfur is to oxygen is 0.629 upon 0.629 equal to 1. 0.629 upon 0.629 is equal to 1. and 2.516 upon 0.629 is equal to 4. Hence, empirical formula is copper sulfate. Empirical formula mass is 62 plus 32 plus 16 multiplied by 4 is 159. Molar mass is equal to empirical mass. Since molar mass is molecular mass, molecular formula is equal to empirical formula is equal to copper sulfate. Chemical reaction and stoichiometry calculations. Calculation based on balanced chemical equations are known as stoichiometry calculation. Balanced chemical equation is symbolic representations of a chemical reaction. It supplies the following informations, which is useful in solving problems based on chemical equations. First, it indicates the number of moles of the reactant involved in a chemical reactions and a number of moles of the product formed. Second, it indicates the relative masses of the reactants and products linked with a chemical change. And third, it indicates the relation between the volume of the gaseous reactant and product at STP. 2.5.1 Stoichiometry problem. Generally, problems based on stoichiometry are of the following types. A. Problem based on mass relationship. B. Problem based on mass volume relationship. And C. Problem based on volume volume relationship. Step involved in problem based on stoichiometric calculations. First, write down the balanced chemical equation representing the chemical reactions. Second, write the number of moles and the relative masses or volume of the reactants and product below the respective formula. Third, relative masses or volume should be calculated from the respective formula. Mass referring to the condition of STP. Fourth, apply the unitary method to calculate the unknown factors as required by the problems. Problem 2.11. Calculate the mass of carbon dioxide and water found on complete combustions of 24 gram of methane gas. Atomic mass carbon 12U, hydrogen 1U, oxygen 16U. Solution. The balanced chemical equation is methane react with 2 moles of oxygen to 2 carbon dioxide, 2 moles of water. We get 16 gram methane, 64 gram for 2 moles of oxygen, 44 gram for 1 mole of carbon dioxide, 36 gram for 2 moles of water. Hence 16 gram of methane on complete combustion will produce 44 gram of carbon dioxide. 24 gram of methane is equal to 24 upon multiplied by 6. 24 upon 60 is multiplied by 44 equal to 66 gram of carbon dioxide. Similarly, 16 gram of methane will produce 36 gram of water. 24 gram of methane is equal to 24 upon 16 multiplied by 36 is 54 gram water. How much calcium oxide will be produced by decomposition of 5 gram calcium carbonate? Solution. Calcium carbonate decomposes according to the balance equation. Calcium carbonate under thermal decomposition give calcium oxide plus carbon dioxide. Calcium carbonate is 100 parts, calcium oxide is 56 parts, carbon dioxide is 44 parts. So 100 grams of calcium carbonate produce 56 grams of calcium oxide. Therefore, 5 grams of calcium carbonate will produce 56 upon 100 is multiplied by 5, which is 2.8 grams of calcium carbonate. How many liters of oxygen and STPs are required to burn completely 2.2 grams of propane? C3H8. How many liters of oxygen and STP are required to burn completely 2.2 grams of propane? Solution. The balanced chemical equation for the combustion of propane is C3H8 react with 5 moles of oxygen to give 3 moles of carbon dioxide and 4 moles of water. Where 1 mole of ideal gases occupy 22.4 liter of volume. Thus 44 grams of propane require 112 liters of oxygen for complete combustions. 2.2 grams of propane will require 11.2 upon 44. Multiply by 2.2 is equal to 5.6 liter of oxygen at STP for complete combustions. Problem 2.14. A piece of zinc weighing 0.635 gram when treated with excess of dilute H2SO4 liberated 200 cm3 of hydrogen at STP. Calculate the percentage purity of the zinc samples. Solution. The relevant balance chemical equation is zinc multiplied by H2SO4 gives zinc sulfate plus hydrogen. It indicates that 22.4 liters of hydrogen at STP is equal to 65 grams of zinc, where atomic mass of zinc is equal to 65 U. 0.200 liter of hydrogen at STP, 65 gram upon 22.4 liter multiplied by 0.2 L liter is equal to 0.68 gram. Percentage purity of zinc is 0.58 upon 0.635 multiplied by 100 is equal to 91.33 percentage. Limiting reagent. When a chemist carry out a reaction, the reactants are not usually present in exact stoichiometric amount, that is in the proportions indicated by the balance equation, because the goal of a reaction is to produce the maximum quantity of usual compound from the starting material. Frequently, a large excess of one reactant is supplied to ensure that the more expensive reactant is completely converted into the desired products. The reactant which is present in lesser amount get consumed after some times and subsequently no further reaction takes place, whatever be the amount left of the other reactant present. Hence the reactant which get consumed limit the amount of products formed and is therefore called the limiting reagent. Consider the formation of nitrogen dioxide from nitric oxide and oxygen. 2 moles of nitric oxide react with oxygen to give 2 moles of nitrogen dioxide. Suppose initially we have 8 moles of nitrogen oxides and 7 moles of oxygen. One way to determine which of the two reactant in the limiting reagent is to calculate the number of moles nitrogen dioxide obtainable from the given initial quantities of nitrogen oxide and oxygen. From the preceding definitions, we see that the limiting reagent will yield the smaller amount of the products. Starting with the 8 moles of nitrogen oxide, we find the number of nitrogen dioxide produced is 8 mole nitrogen oxide multiplied by 2 moles nitrogen oxide upon 2 moles of nitrogen oxide is equal to 8 mole nitrogen dioxide and starting with 7 moles of oxygens. The result number of moles nitrogen dioxide formed is 7 moles oxygen react with 2 moles of nitrogen dioxide upon 1 moles oxygen is 14 mole nitrogen dioxide, because 8 moles of nitrogen oxide result in a smaller amount of nitrogen dioxide. Nitrogen monoxide must be the limiting reagent and oxygen is the excess reagent before reaction has started. Urea is prepared by reacting ammonia with carbon dioxide. So 2 moles of ammonia react with carbon dioxide to give urea and water. In one process, 7.2 gram of ammonia are treated with 1142 gram of carbon dioxide. A. Which of the two reactant is a limiting reagent? We calculate the mass of urea formed. See how much excess reagent in gram is left at the end of the reactions. Solution. We carry out two separate calculations. First, if 637.2 gram of ammonia react completely, Calculate the number of moles of ammonia of urea that could be produced by the following relation. Mass of ammonia q moles of ammonia q moles of urea, which is moles of urea give 63.7.2 gram ammonia, multiply 1 mole ammonia upon 17.03 gram ammonia, multiply by 1 mole urea upon 2 moles of urea, 2 moles ammonia, we get 18.71 mole urea. Second, the relation from 1142 gram of carbon dioxide, mass of carbon dioxide, moles of carbon dioxide, moles of urea, number of moles of urea that could be produced if all the carbon dioxide reacted. Moles of urea is 1142 gram of carbon dioxide multiplied by 1 mole of carbon dioxide upon 44.01 gram carbon dioxide multiplied by 1 mole of urea upon 1 mole carbon dioxide equal to 25.95 mole urea. It follows therefore that ammonia must be the limiting reagent because it produces a smaller amount of urea. B. Molar mass of urea is 60.06 gram. We use this as conversion factor to convert from moles of urea to gram of urea. Mass of urea is equal to 18.71 urea multiplied by 16.06 gram urea upon 1 mole is equal to 1124 gram urea. Starting with 18.71 moles of urea, we can determine the mass of carbon dioxide that reacted using the mole ratio from the balance equation and the molar mass of carbon dioxide. Continue on next page. The conversion steps are moles of urea give moles of carbon dioxide give grams of carbon dioxide. So that mass of carbon dioxide reacted to give 18.71 mole urea multiplied by 1 mole carbon dioxide upon 1 mole urea multiplied by 44.01 gram carbon dioxide upon 1 mole carbon dioxide gives 823.4 gram. The conversion steps are moles of urea use moles of carbon dioxide and grams of carbon dioxide. So that mass of carbon dioxide reacted 18.71 mole NH2CO urea multiplied by 1 mole carbon dioxide upon 1 mole urea multiplied by 44.01 gram carbon dioxide upon 1 mole carbon dioxide equal to 83.4 gram. The amount of carbon dioxide remaining in excess is the difference between the initial amount 1142 gram and the amount reacted is 823.4 gram. Mass of carbon dioxide remaining 1142 gram minus 823.4 gram is equal to 318.6 gram is equal to 319 gram. Concentration of solution. A majority of reaction in the laboratories are carried out in a solution. Therefore, it is important to understand how the amount of substance is expressed when it is present in the form of a solution. The concentration of a solution or the amount of substance present in a given volume of a solution can be expressed in any of the following ways. Part 1. Mass percent or weight percent W upon W percent. Second, mole fraction. Third, molarity. Fourth is molality small m. Mass percent. It is obtained by using following relations. Mass percent is equal to mass of solute upon mass of solution multiplied by 100%. Problem 2.10. A solution is prepared by adding 2 gram of a substance A to 18 gram of water. Calculate the mass percent of the solute. Solution. Mass percent of A is equal to mass of A upon mass solution multiplied by 100 is equal to 2 gram upon 2 gram of A plus 18 gram of water multiplied by 100 gives 2 gram upon 20 gram multiplied by 100 is 10%. fraction. It is the ratio of number of a mole of a particular component of a solution to the total number of moles of the solution. If substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the moles of fraction A and B are given as mole fraction of A is equal to number of moles of A upon number of moles of solutions. Mole fraction of A is equal to Na upon Na plus Nb. Mole fraction of B is equal to number of moles of B upon number of moles of solution is equal to Na upon Na plus Nb. Molarity. It is the most widely used units and is denoted by capital M. It is defined as number of moles of the solutes. It is defined as It is the most widely used unit and is denoted by capital M. It is defined a number of moles of solute present in 1 liter of the solution. Thus, molarity capital M is equal to number of moles of solute upon volume of solution in liter. Problem 2.17. Calculate the molarity of sodium hydroxide in solution prepared by dissolving its program in enough water to form 250 ml of solutions. Solution. Since molarity M is equal to number of moles of solute upon volume of solution in liter, capital M is equal to mass of sodium hydroxide upon molar mass of sodium hydroxide upon 0.250 liter. Capital M is 4 gram upon 40 gram upon 0.250 liter. M is equal to 0.1 mole upon 0.250 liter. So capital M is 0.4 mole per liter is equal to 0.4 molarity. Note that the molarity of a solution depends upon temperature because volume of a solution is temperature dependent. Molality. It is defined as number of moles of solute present in 1 kg of solvent. It is denoted by small m. Molality small m. Number of moles of solute upon mass of solvent in kg. Moles. That molarity of a solution does not change with temperature since mass remain unaffected with temperature. Often in chemistry laboratory, a solution of desired concentration is prepared by diluting a solution of known higher concentrations. The solution of a higher concentration is also known as stock solution. 2.1. The density of 3 molar solution of sodium chloride is 1.25 gram per ml. Calculate the molarity of the solution. Molarity is 3 mole per liter. Mass of sodium chloride in 1 liter is 3 multiplied by 58.5 is equal to 175.5 gram. Mass of 1 liter solution is equal to 1000 multiplied by 1.25 equal to 1250 gram. Density is equal to 1.25 gram per ml. Mass of water in solution is equal to 1250 minus 175.5 is 1074.5 gram. Molality is equal to number of moles of solute upon mass of solvent in kg is equal to 3 moles upon 1.075 kg is equal to 2.79 molality. Use of graph in analysis. Use of graph in analysis. Analytical chemistry also involves deducing some relation, if any, between two or more properties of matter under study. One of the classic examples in the relation between temperature and volume of a given amount of gas, a set of experimentally measured values of volumes and temperature for definite mass of a gas upon plotting on graph paper appeared as in the figures when the points are directly connected zigzag patterns. Result from 22b. From the pattern, no meaningful result can be deduced. A zigzag pattern results due to many types of error that occurs in many measurements involved an experiment. Figure 12.2c show a smooth curve which may be called an average curve passing through this point. In the above example, it happened to be straight line. Interference is that volume is directly proportional to temperature. Drawing an average curve through the point on graph. While fitting it to the smooth curve, care is taken that the plotted points are evenly distributed about it. Mathematically, even distribution is understood as follows. From each point, draw a perpendicular to the curve. The perpendicular represents deviation of each point from the curve. The positive deviation are shown in red and negative deviation are shown in the blue. Take sum of all the red perpendicular and the blue perpendicular separately. If the two sums are equal or nearly equal, the curve drawn show the experimental point in the best possible representations.